right, hello you guys. I'm out for today. I know a lot of you guys are also out on the band field trip, so wherever you are catching up with our lesson for today, we're going to go over some applications, formulas that exponential functions are used with. So go ahead and get started on the warm-up. So write down these two equations, solve them, check to see how you're doing with the neighbor, and then um, take a moment, pause the video, work on your problems, and then play the video when you are ready to check your solutions. All right, so solving the first one, it's an exponential equation. Noticing that 9 and 81 could be rewritten at common bases, common base here with 9. Once you have that, then you go ahead and set your exponents equal to each other and find that x equals -3. Second equation, we have a log, and noticing you have two log expressions, so condensing them into one through division, and then turning that into an exponent. Obviously, when we have just log, our base is 10, so you'd have 10 to the first equals x over 9, x plus 9 over x, and then solving, you get x equals 1. And checking your work, not just to make sure for your extraneous solutions, but just to, make sure you got the question right. Checks in red. So we're going to be working on our application questions today. We're going to go over a couple of different scenarios where you could have either appreciation or obviously something could depreciate. And then you'll have a classwork assignment. And then when you're done with that, you could be working on Delta Math or JLab assignments. So for appreciation or depreciation, exponential growth and decay functions are used in a lot of business to calculate the appreciation or depreciation of different assets. So in your growth or decay formula, growth meaning exponential growth, decay meaning exponential decay. So think that if your value is going to be increasing growth, decreasing decay. You have A, which means the amount of your asset after a certain time, equals P. So P is your principal. That is the starting amount that you're investing maybe, or starting amount if you have a population that's growing at an exponential rate. That's always the starting amount. You're going to multiply that by 1 plus or minus your rate, and that will be your base. So plus, if it will be growth or appreciation, minus for decay or depreciation. And that rate we're going to turn into a decimal if it's given as a percent. And we are going to raise it to T, which will stand for time. So you'll use the same unit as the time as your rate. So if your rate is annum, which means yearly, then your time has to be in years. So example 1, in 2016, I did buy a new car, and I'm looking to sell my car later this year, and to upgrade to get a larger model. So I have a sedan right now. I'm probably going to look to get an SUV. So I'm kind of trying to think about, okay, well, I bought my car for $30,000, and cars depreciate around 15% per year. So I want to know, how much is my car worth this year? So thinking about our formulas we just discussed, I'm going to think about keyword here of depreciate. My value of my car is going to be decreasing over time. So using our formula, A times 1 minus my rate raised to the T. So minus was my first choice I had to make, noticing that I depreciate. Let's figure out what will that amount be today. So P stands for my principal, the starting amount, which was what I purchased my car for, which is $30,000. And I have 1 minus my rate, which is so 0.15. And I'm gonna raise that to my time, which if I bought it in 2016, and I wanna know what it's the value in 2024, my time will be 8, so 8 years. So go ahead and put that in your calculator to figure that out. Pause the video and then check when you're done. And I just rounded to the nearest dollar amount. So when you are entering that into your calculator, remember your exponent, use the caret button, which is below clear. And my car I'm finding is going to be worth about $8,175 to the nearest dollar, which is not a bad amount if I'm looking to put that down for a new car payment. Alright, let's look at example 2. The population of Reston increases by 2% per month. So noticing that 2% per month, you may read. If there were 90,000 people in Reston in 2018, how many are there in 2022? So, if my population is increasing, I know that that will be growth or appreciation. So my formula would be A equals P times 1 plus my rate raised to the time. And my principal, that starting amount, the amount of people in the first year that I'm looking at, which is 2018. I'm going to add that to my rate of 2% per month, which is 0.02. Now remember that that was per month. And if I have starting in 2018 and going to 2022, I know that is 4 years. But my T has to be in months because that is what my rate is given in, which means my T is going to be 48 months. So go ahead, pause the video, see what the population will be in 2022. As always, a couple things to keep in mind. Answering in context of your problem. So like if you do have money at last, how long I just round into the nearest dollar? You know, if I'm thinking about putting down a car payment, I'm probably not as precise as like putting it down to the nearest cent. Here, with the amount of people, obviously I want to have a whole number for the amount of people. I can't have a decimal of a person. So, keeping that in mind as you're working on your problems. Alright, so a lot of applications for our exponential functions are going to be coming from compounding interest. So our compound interest formula, we can have two different scenarios. Our first scenario is A equals P, where P is still your principal, and your A is like your amount that you want to know that's like your investment after a certain amount of time. You're always pretty much just only going to be using the addition symbol here because it's going to be an investment. So thinking about like if you're investing something into a bank account or like a savings account, you have like an interest rate, and that is going to be increasing over time because banks want you to put your money into their accounts. They're going to give you money back over time. So your R would be your rate per year. Remember, with our compound interest, it's always per year. And N is going to be the number of payments in a year. So with our compound interest formula, with your N, you're going to have different situations for your problem. It might say monthly. That would mean your N would be 12. Obviously, like quarterly, that would mean 4 times a year. Weekly, like 52. You know, like all those different situations. 52 weeks in a year, like, you know. So reading the context of the problem for your end value. That means like how many times you're compounded for your like, however many times, like, I know thinking about like my bank statement, right? It's probably monthly. Honestly, I haven't looked too much into it because I like get a new bank statement like every month. Like, oh, this is your interest that your savings account has accrued over this month. So I would be like, okay, well, like it's happening monthly. And T is your time always in years. So compounding continuously with this formula, P, R, and T are still the same values from your interest formula. Just notice now instead your base is E. So it's P times your base of E raised to the RT, where E is that value, Euler's number that we've talked about before. Compounding continuously means that your interest is constantly accruing over time. So let's check out example 3. You deposit $4,000 into an account that pays 2% interest compounded monthly. How much will you have after 5 years? So obviously this phrase here, big key idea, compounded monthly, which means I would be using the following formula. My compound interest formula, not continuous. A1 plus my R over N raised to the NT. So let's go through and kind of figure out what are all my values. So $4,000, that's my initial principal. And this pays 2% interest, which is my rate, so 0.02. And it's over my N. If I'm compounded monthly, that means that's going to happen 12 times a year, 12 months in a year. So over 12, and that's going to be raised to the N times T. So 12 times my T would be 5, because I want to know how much money will I have after 5 years. So pause the video, calculate that, and once again, if you want that nice fraction in your calculator here, where it gives you this box over box, alpha, y equals, and then hit enter after. So go ahead and calculate that, and pause the video, play when you're ready to check your answer. Alright, so after 5 years, you would have $4,420.32 into your account now. Alright, one more example. Example 4, you deposit $1,500 into savings account that pays 4% interest compounded continuously. How much money would you have in your savings account after 3 years? So key phrase here, compounded continuously, which means we're going to have A equals P-E-R-T. Sometimes you might hear it referred to as PERT. And let's go through and see what are each of our values. So P, your initial deposit investment, $1,500. Multiply that by E, raised to your rate of 0.04. And our time here is 3. So pause the video, calculate that, and then play when you're ready to check. Alright, so you should get $1,691.25. So remember, if you want to get that E value in your calculator, it's second ln. You'll have E, and you'll have to be able to raise it to some value, which in this case here, you can just put 0.04 times 3. Alright, you guys, that wraps up our lesson examples for today. So what you're doing from here is that applications classwork. You'll grab a copy of it from the sub when you're ready, and you'll check the key on Schoology. You're welcome to work with people at your table. And after that, things you can be working on when you're done. You're solving Delta Math homework, or if you still needed to finish any other Unit 7 homework, remember that has to be done by the day of your test. You could also be working on your JLab number 1, or any other retake things you might need to do. And as always, email me, stop by if you have any questions on anything you're working on.